All right, so welcome back. This is our second talk on the frames and machines discussion in statics. All right, this particular topic is pulleys. And if you ask any practicing engineer, the problems that were always the trickiest that seemed to confuse them back when they were in school, pulley problems and those darn block and tackle problems seem to be near the top of the list. Okay, so what I figured I'd do in this particular lesson is I kind of walk you through how a pulley works, the statics that go behind it, and then we'll talk about those block and tackle problems and how you start to address solving those. All right, so basically a pulley is a mechanism that redirects a force. Okay, typically we think of a pulley as being a round object that rotates. Okay, so if I draw just a simple one that looks something kind of like this, okay, we would have our pulley as this round object, and generally there's a bearing or a shaft or something that's connected to another member that allows this thing basically to rotate in some direction. If T2 is greater than T1, it rotates clockwise, and if it's the other way, T1 greater than T2, it goes the opposite direction. Okay, now most statics classes and really in most engineering problems, a lot of times we assume pulleys to be frictionless, okay? And so there's some friction values that would occur at a number of locations. We could get friction in the bearings, we could get friction of the cable as it moves past the pulley, all sorts of places. So just to kind of get our heads wrapped around the mechanics and the basic statics equations, we're going to neglect friction for all cases in this. Now, when we get to our friction topics later on in the series, then we'll reintroduce pulleys and wrap angles and things like that in which T1 doesn't equal T2, but for now T1 is assumed to be equal to T2. All right, so what we have here is that, and you'll notice that in this particular case I've got a rope that comes off with a force of T1, okay, and then it wraps part of the way, but not all the way around, but just enough to change the direction of this guy, if that's my force T2, enough to change my direction of him by some angle theta, and we're going to measure theta off the horizontal. You can measure from anywhere that you want, it doesn't really matter, but the idea is that that's what the system is happening. All right, so the way that we tackle pulleys are unique in that they are always statically determinate, okay? And if I pull this pulley system off of the member that it's connected to and take the rope with it, I get a free body diagram that kind of starts to look like that. All right, so if I slide this up a little bit, it'll look something kind of like this. So this is the pulley free body diagram. All right, now the connection that we had up in the middle, pulley pins are almost always considered to be pins. Okay, the shafts they're free to rotate, but they can't move in the X and they can't move in the Y direction. All right, so if I draw a free body diagram of that, and we follow our Y's, self weight, internal, the internals are T1 and T2, supports are EY and EX, those are the pin reactions, and then external forces, there aren't any external forces actually acting on this particular system. All right, so the free body diagram looks something kind of like this. No major surprise. All I'm doing is I'm adding those pin forces EY and EX. Okay, and when I do that, I can go and I can start to write our equations, just for basic sum of forces X, sum of forces Y. Okay, now again, sum of moments doesn't do anything for you, assuming that the pulley is round, because the distance from here to here is the radius of the pulley, but it's also the same from here to here. Okay, and so if T1 and T2 are the same value, then this moment produces a counterclockwise moment, and this one produces a clockwise moment. They're the same value, and they cancel. All right, so the moment equation doesn't do us any good on pulleys. Now, if you got into an advanced mechanism like a cam or a flywheel or something like that, maybe you could end up getting a moment transfer in the system that causes it to kind of behave a little bit differently. But again, for a basic statics class, we're not going to worry about that. All right, everything else is basically the same as what we've always done. Sum of forces X equals 0. I'm going to assume to the right positive. Minus T1 plus EX plus T2 cosine theta is all equal to 0. That gets me 1. You'll notice that if T1 equals T2 and I know the angle, I know everything except for EX. All right, so I can find the value EX. Okay, and then likewise in the Y direction, I could do EY up minus T2 sine theta, all equal to 0. Again, I know T2, I know theta, I can find EY, and so I can find those two reactions. And that's handy because what I can do then is I can pull the pulley off and get rid of T1 and T2 and basically put the reaction EY and EX in the opposite direction. Because remember, the pin that we have, if this is my pin, kind of like what we did with the method of joints, I get an EX this way, I need an EX this way. Okay, and if I need an EY this way, I need an EY this way, so forth and so on. Okay, so equal and opposite, equilibrium across the pin, because the pulley pushes on the pin and the pin pushes on the other member. So just like we did in the last lesson with the frames and machines, it's the same approach. All right, so my EY I assumed up here, it is now down here, and I assumed to the right here, it is now to the left here. Okay, and then I can go on and draw the free body diagram of just this piece, and I can completely ignore the pulley. And I can greatly simplify some of the geometry, and then I don't even have to worry about the radius of the pulley and how far away these forces are. Okay, now there are times that you don't want to do that, but for the most part, that's generally the approach, is pull the pulleys off. Now the one thing that you got to be worried about when you pull off T1 and T2 and go to this bar approach is if T1 and T2 are tied to your structure at some other point, I have to start worrying about where is that force coming in, because I've cut it now, and we'll show you an example a little bit later about how we start to account for those. Okay, so you're always kind of worried about, and that's kind of like my last note on this. Okay, is that EY and EX can always be found, but beware of any connections T1 and T2 may have to your structure, because they can put forces into other parts of the structure, and that's not uncommon. All right, so that's kind of basically what a pulley is. All right, now, pretty easy to solve. The problems that most engineers recall and dread, because on just about every statics test of some sort, there's always been a block and tackle problem. And what this is a system of pulleys. Okay, and so if we have a basic apparatus that looks something kind of like that, let's see if I can zoom ourselves out here a little bit. Looks something kind of like that. Okay, what I have is I have an apparatus, and part of the problem with these block and tackle problems is that they're very complex and they're kind of hard to decipher what's going on. But I'll try to explain it as best I can. All right, what I have is I have a system of 3 pulleys. Okay, I have a pulley A, a pulley B, and a pulley C, and I have this rope that's being pulled on with a force P that wraps all the way around A, comes down around C, wraps back up around B, okay, and then is tied off at the center of C. Okay, and then at C, I have a bar on which a weight is hung. Okay, so this is some sort of lifting apparatus. I also have, in order to keep this thing from collapsing on itself, is I have a rigid bar, my bar number 1, that is fixed at the ceiling. Okay, and then pulley A is in a hole on bar 1, and pulley B is in a hole on bar 1 also. All right, and this kind of keeps the whole system from wanting to kind of collapse in on itself. All right, so just like we did before, we're going to look at what can we do to be able to solve this problem. Okay, and so we're going to go through, and the first thing we're going to do is we're going to draw the free body diagrams of all the parts of this particular system. All right, for us, in this particular example, we want to find the force P here that's required to lift this W, okay? And we'll see what happens. Okay, all right, so basically, again, we're going to assume the pulleys are frictionless, okay, and I'm going to go pulley by pulley, and we're going to look at these. Okay, so the first 2 that we're going to look at on this here are the pulley at A, and basically usually what I do is I start at the load and I draw my free body diagram of a pulley, okay, and then I basically just follow that rope on around. Okay, so I start at the free end basically, and we look at it. So if we go through and look at our definition for this pulley, so we have our pulley, and here are my reactions A, Y, and AX that are happening at the shaft on this thing. Okay, and on the left side of this I have a force P that's pulling down. Okay, that was my external force from the original system. Okay, and then in order to pull the system out, I had to cut the shaft. That revealed A, Y, and AX, and then I had to cut cable T. I had to cut this rope over on the other side. So I cut the rope, and I just call that arbitrarily as T1. Okay, now if we recognize our definition of a frictionless pulley, the force on this side has to be equal to the force on this side. Okay, we don't care about the direction, just the magnitude of the forces are the same. So we actually know T1 is P, but we'll show you that a little bit later. Okay, then we come on and we go to the next piece. Okay, and in this case I'm jumping down to C, because again I'm just kind of following this rope up and around and coming back down this side. So I'm coming into this member and I'm going to cut him out, and let's look at what happens. Now I'm going to cut this one a little bit differently. Instead of cutting the pulley out and dealing with the reaction CY and CX, I'm going to basically cut everything and keep the weight W. So I'm going to cut this rope, and this rope, and pull the whole system out. Okay, so this is one of the tricks on how we start to kind of figure out what we can cut and what we should and shouldn't be cutting free. So when I do that, when I keep it like this, okay, again, I still have that pin in there, but the forces are balanced because I haven't cut the pin. All right, so I have my T1, and notice that this rope was T1. It had to match the one that was over here because that's the same rope. Okay, and then I truck on around to this one and then up the other side, and I cut it. I have another tension that shows up on this guy, so we'll just call it T2. okay? And then I also cut this rope that's tied off somewhere, further up on this, and so T3 is the tension that we're going to say in that force. Now again, these are all ropes, so all the forces are tension. They're always pulling on the object, so every one of these is pulling on the end of the rope. Okay, and then likewise, I have my external force W hanging off the bottom of this bar, and that's a valid free body diagram. Okay, all right. So the next piece then is I can come in and I can look at the pulley at B. Okay, and so I know it's a lot going on here. Okay, and so just like we did before, I've come in, now I'm coming in, I've cut that T2. This T2 is the opposite of the one that we saw happening up here, and then it wraps on up around this bar. Okay, and then I have my T3, which is the rope on the other side. Now, in order to get this guy out, we had to do something a little bit differently. I could choose to do what we did over on pulley C and basically cut the bar. But the problem is that the bar member, if you remember back up here, this bar, okay, is a rather complex entity, right? It's not a two-force member because I have a pin here and a pin here, okay, and then I also have a fixed connection here. So this thing is experiencing bending and doing all sorts of strange things, so I can't make any assumptions. And so I know we haven't talked about this yet, but when that happens, if I cut something, I always get three unknowns. I get an internal moment, I get a horizontal force, and I get a vertical force that shows up at the new cut location. So that's kind of an ugly little mess that just happened when I do that. Okay, so on this one, instead, I'm going to choose to cut it through the pin and reveal the pulley by itself. Okay, and when I do that, I get my T2 and T3 again, and then I get those pin reactions just like we did back up on, up on pulley A. All right, and so when I do that, this is actually a simpler structure to solve than this one. Okay, I mean I had three unknowns here, I only have two here, so that's a good trade. All right, so a lot of times, if it's just a pulley, I pull it out by itself, but sometimes I keep it and sometimes I don't. It just takes a little bit of practice and a little bit of experience to understand what it is that you're going to do. So those are my free body diagrams of the pulleys. Now, I can go in and I can also draw a free body diagram of that main bar that we had happening up at the top, the bar that contains B and D. All right, so if I came in and I looked at this bar here, okay, and so when I do that, the free body diagram of this bar, you'll notice is that we had where the pin was connecting at A, and I had where the pin is connecting at B, and then I get my moment at D, I get my dy, and I get my dx on that guy. All right, and so again, all we're doing is taking equal and opposites. So if AY was up here, I put AY down here. If AX is to the right here, I put AX to the left. Okay, and then BY down here corresponded to my BY up here. Okay, and then my BX over to the right. And I just realized I drew that in the wrong direction. See how easy it is to do? All right, so I'll put BX over to the left on that one. That's okay, I don't do anything with it in this example, but that's fine. Okay, so BX opposite and opposite. Okay, so it's easy to do. I mean, like you saw it, I made that mistake myself, so it's really easy to mix that up. All right, now once I have all of those pictures done, then I can go in, okay, and I can start to look at my free body diagrams. All right, so as we started to kind of chase those forces around on my bar, let's get this under here so we can see a little bit, try to maintain the pictures of these. Okay, so if I go look at pulley A, you can see that we said that by definition P had to be equal to T1. No problem. Okay, and then from pulley C, that's the one over here. Okay, we said that the rope that wraps around the outside, T1 had to be equal to T2. And since we knew that T1 was equal to P, we know T2 is also equal to P. Okay, and then from B, which was the one down on the bottom, this one, okay, we know that, again, the rope wraps around pulley B, so T2 has to be equal to T3, and we found that T2 was equal to P up in this equation, so T3 is also equal to P. So what happens is if you look at this system, the entire system of this thing on here, I pull this force P, and that P travels all the way around through the rope until it reaches its termination point, all right? So the tension in this rope is P, the tension in that rope is P, and the tension in that rope is P. Okay, and what that allows us to do is it allows us to go back, okay, and examine this free body diagram, because every one of these guys is now a P. And this is that external weight that we had. So again, we don't know the value. It could be 1,000 pounds or 50 newtons or whatever. We can come up with that. But what I can do with that is I can go in and on that pulley Let's see, I can write the equation that we just saw that says that, okay, all my T1, T2, and T3 were all acting upwards, so positive T2 plus T3 plus T1 all acting up, minus the W all have to be equal to 0, because again, we're bound by the rules of statics. All right, and so P plus P plus P is equal to W, so W is equal to 3P, so the force required to lift that weight W is W divided by 3. And that's it. That's all there is to it. So in order, if I had 300-pound weight I wanted to lift, the way this assembly was made on there, all I would take to lift this thing is 100 pounds. Okay, and that's what gives us what we call a 3 times mechanical advantage, right? I put in 100 pounds of work into my apparatus, I get 300 pounds of work on the outside end of it. Okay, and so that's so now the more times I wrap that rope around, the more times I build this number. And so that's how you can actually design an apparatus. And this was common, in farm country, in barns when lifting bales of hay is the old stereotype example. But you just take a rope and wrap it 7 or 8 times around a couple of pulleys and pull it, and boom, I can lift things that you normally can't lift. Okay, and that's the definition of what mechanical advantage is for us here. Okay, now just for fun, let's go look and see what we can do. Say we wanted to find that vertical reaction at D. Okay, all right. We could go back and we could chase through and get that bar free body diagram that we had here, and I could come back to this picture and kind of look at it, and I would have to find BY and BX, and I could get those from pulley B, and I could get AY and AX from pulley A, and then I could come in and start to try to solve all of the stuff that's happening for the 3 unknowns that were happening up at the top. But I'm going to show you another way to do it. Okay, it's a little bit easier, maybe a little bit simpler. Now, if you remember in statics, we really don't care what the shape of the objects are. Okay, these equations that we're writing, all they take into account are the forces and the location of those forces. All right, so if I went in and wanted to find, these 3 effects that were happening up at the top, this may be the apparatus where it's tied to the ceiling, or that overhead, barn roof, rafter beam, whatever it is that I'm using to hold the apparatus in place. Okay, and I could draw something that looks like this. The only things that matter on this is I could draw a free body diagram of the entire system on here. And notice, I didn't cut anything. I didn't cut the pulley A, B, or C. But if I know the location of the force P with respect to that vertical line, and I know the location of W with respect to that location on here, I have everything I need to be able to analyze this problem. All right, so I'm just going to, for fun, I'm going to call this as E sub P, the eccentricity for P, and this is the eccentricity for W. Okay, and so to find dy, all I do is write the sum of forces y is equal to 0, and so I take all the forces that are in the vertical direction, so I have a positive dy, that's this guy, I have a minus p, that's that one, and a minus w there, and this whole thing is in equilibrium, so I have to set that equal to 0. And so what happens is I can solve for dy as being p plus w. Okay, well, we saw that P is P, okay, and W we saw from before was 3P, so the reaction at the roof of the ceiling should be P plus 3P or 4P. All right, so if P is 100 pounds, then the reaction at the ceiling needs to be 400 pounds. And that should make sense, right? I've got an apparatus that's pulling down of 300 pounds, and I pull on it with another 100 to lift this guy on here. That's 400 pounds total acting on this thing, right? Okay, now, forces in the X for this particular apparatus, because my rope was vertical, is just simply dx equal to 0. Now, if this rope had been kind of off at an angle or something, you would get an X component that would show up on there. Okay, so again, his orientation, his direction, and his location are very, very important in solving this. What's a little interesting is the moment equation for this guy. All right, and so all I'm going to do is I'm going to sum moments up here at the top at D. All right, and when I do that, I get rid of dy, I get rid of dx, and only the md will show up. Okay, and so the moment that this thing causes is that P times E sub P, okay, that's the distance this fort makes from this point right here, okay, so that's P times E sub P, plus the distance, and it's drawn a little small, but you can see I have whatever that location is, EW and W is the moment that causes, that's this guy, okay, plus whatever the induced moment at the ceiling is on this thing, all right, and so that's my MD value, okay. Now, if this had been pinned at the top, meaning that there was no moment on this thing, MD was equal to 0, this term would go away. Okay, and so something interesting happens if I just kind of cover up the M and we look at that equation that we have. P is a positive value, W is a positive value, E is clearly positive. The only way that I can make this expression equal to 0 is for EW to go negative. Now, we assumed a positive E was that way. All right, so in order to balance this thing and provide equilibrium on a system that is pinned at the top, when I pull this rope down this way, this whole apparatus kind of rotates such that this force will slide over to here somewhere. Okay, and give me a negative EW times that force plus the P times that one, and that will give me the moment balance that happens. So you can get into some kind of advanced studies on moment equilibrium that come out of some of these systems. Now, if the bar is rigidly attached, this guy shows up, and then EW can be whatever it wants to be. It won't experience that kind of rotational effect. So it's kind of a little side effect, kind of an interesting little tidbit that I thought I would share with you. Anyways, I hope this kind of gives you a little bit of a lead in to how to tackle block and tackle problems. A little ironic, isn't it? Okay, so yeah, I guess that will about do it. Again, it's just a matter of pulling apart the pulleys and drawing them individually, and then learning some of the strategies for how do I pull pieces off and put pieces back on, and how do we start to analyze. And again, that just kind of comes with practice. So the more you work these, the more experience you get, the easier it'll be, and you'll be ready for that next statics quiz. And then you can laugh at those old timers that say, hey, these are really, really hard, because really, if you understand the basics, they're pretty simple. So anyway, hope this helps. Stay tuned for more frames and machines in the next video. Thanks. Bye.